we were discussing about the output and steady state errors of various types of systems. Based on the types of system, we saw that if the system is of type 0 and type 1, right, the corresponding steady state errors are like this. Okay, now we'll go for the type 2 system, where we'll write the G into H as follows. Correct. So the G of S. Okay. So please provide me the answers. When the input is, so if R of S is equal to 1 by S, what was the ESS? Okay. ESS becomes equal to 0, correct? 1 by S cube, the steady state error becomes equal to a constant, right? Okay, so this is the value of ESS, right? Okay, now fine. Next, we'll directly go to the stability analysis. Okay, now let's define what is meant by stability. Uh, Now, stability. Can you try to define stability? When you can call a system as stable, in terms of under what condition? Under what condition they should not be affected? What is the condition at which we can say that the system is stable or non-stable, right? So stability has to be defined under some condition, right? Correct, correct. I will write finite input, right? That's what is a smaller number, right? It's a finite input. Finite input should produce a finite output, right? I think this is what you meant. When you give a input which is known value, output should also be this. This is one way of defining. Yes. Now let us say that I'm giving an input value of 2. Output is also finite, say 10, 20, 100, some known value. This is the first way of defining stability, right? When the system is something like instantaneous, like you give an input, immediately you get an output, right? Under such condition, this definition holds good. Okay, but there are some cases where the system is not instantaneous. Okay, so whenever the system is not instantaneous, in the sense it actually its output depends upon the past inputs and the past outputs. Possibly, whenever you try to represent the differentiation in terms of the differential equations, the meaning is that. So you see, the output is not just dependent on x of t, it is dy by dt, rate of change of your output, correct? Plus d square y by dt square is equal to rate of change of that rate of change. So you see, it actually depends upon more factors than the straightforward input, right? So under such condition, right, we try to define the stability in a slightly different way, right? So that is, we can say, as, because it depends upon the time and your past outputs. So as the time goes to infinity, right, after a long time, right, the output should be finite. So in the sense, right, so the limit t tending to infinity, output is denoted as c of t, right, because r of t is input, c of t is output. That's the standard definition which we use. Should be less than infinity is another condition, right. It says that as the time progresses, right, your output value should be finite. It should be, anyway, the first point says that it is definitely finite, but it should remain finite even after time becomes infinite. Okay, so let's look at the some example just to understand this concept. Okay, because initially it may look finite, but later on it may tend to be infinite. Let's look at some examples. All right, so let's say this is the example number one, where we can see that the system becoming stable. Second example will be system becoming unstable. So let's say, fine. So this is the transfer function, which is the output, that is C of S by R of S. Okay, this is equal to, see, this is 4.5 whole divided by, this is S plus 2.5 into S plus 1.5. And let us say the input, let the input R of S is 1 by S. Okay, it's obvious that I'm giving a step input. Right. So now let us calculate. This implies what is output? Output is a C of S is equal to the transfer function T of S into R of S. That should be 4.5 divided by, this is S plus 2.5 into, this is S plus 1.5, multiply this with R of S, which is 1 by S. Okay, so now we want to go to the C of t. That's why this has to be solved by applying the partial fractions. Okay, so we'll equate this is A divided by S plus B by S plus 1.5 plus C 2.5. Okay, so please calculate the values of A, B, and C. Sure, take your time. Sure, sure. Hmm, okay. S plus. Okay. That's right. 13 S plus. So now, this is the Laplace of the output, isn't it? So we need to take the inverse Laplace to come back to the time domain, right? So we are actually interested in that. That's why we take the inverse, right? Apply L inverse. So we get the C of t as, so this has to 1 by s means we know that it is u of t, right? So this is 1 by 4 into u of t plus 11 by 12. What is the inverse Laplace of 1 over s plus 1.5? So this looks like 1 by s plus a, right? What's the inverse Laplace? Do you remember? Right. This is e to the minus at u of t. Correct? So the next term, this is e to the 1 point min- 1.5t into u of t. In the next term as well, this is 13 over 20 e to the minus, right? Okay, so now from the basics of the system's time response, we know that this part is actually the output, right? So you see, my input is actually u of t, right? But my output is 1 by 4 times u of t, right? Amplitude reduces here. That's okay, that's fine. No issues with that. So what do you call this term? This term, and what is the name for the second and the third term? There is a name for that. Do you remember? I have discussed about that earlier, and I'm not very sure. Let's just check. If we have not discussed, then I'll tell you about that now itself. Okay. Yeah, I think. Yes, you can see here. See, excitation pole, system pole. So corresponding to system poles, you have transient output, and excitation pole gives you a steady state output, right? Okay, that's the name. Anyway, we have discussed, so you already know about that. Fine. So now let's. This means let's check whether the system is stable or not. Because for stability, I need to find this condition. For stability, right? Okay. What was the condition? Condition is you apply the limit. Correct. Limit t tends to infinity. I should find what happens to the c of t. This should be less than infinity. Should be a finite value. Let's check that. So this means let's apply limit the not c, sorry, t tending to infinity. Correct. Limit t tending to infinity c of t in the above equation, right? So this c of t is what I'm trying to find out. So what happens to the first term? The steady state response, it's 1 by 4 into u of t. As t tends to infinity, what happens to this term? It remains same. U of t is 1 only, right? Irrespective of where you are finding. So this simply is 1 by 4. Plus, what happens to the second term? That's 11 by 12 into uh, e to the minus 1.5 t u of t. What happens to that function when t goes to infinity? After a long time, what happens to this term? Anyway, u of t is 1. Just find out what's the value for e to the minus 1.5 t. Huh, okay, okay. Put the t value as a large value or infinity over there. Maybe that will help you out. Hmm. T is very large or t is infinity. Because it is e to the minus infinity. That's a 0. Correct. So 13 by 20 into that's also 0. Correct. So we can see that this value, right, after a long time becomes 1 by 4. Right. So it's less than infinity. So this given system is said to be stable. Okay. Fine. Now let's look at a different different problem. Uh, when we solve this, we will understand that we'll first see that the system becoming unstable, and also we will see that what are the actual condition in terms of the locations of poles and zeros, so that the system becomes stable or unstable. Okay, so for that, let's solve another one. So this is the transfer function is equal to, this is 9 over 26 whole divided by, this is s plus 1 by 17 into, this is s minus 3 by 16 into s minus 6 over 37. All right, this is the transfer function, and let the input once again be equal to 1 by s. We can even consider the other inputs, but I just want to keep the concept clear, and I don't want more mathematics. Okay, if you keep 1 by s square, you go for a different types of solution of the solution of the partial fraction, which might take more time. Okay, so let's avoid that. Let's take a simple input 1 by s. So we know that the c of s is equal to the transfer function into this. So this is 9 by 26 whole divided by, this is s into s plus 1 over 17, s minus 3 by 16, and this is s minus 6 over 37. Alright, so considering this, now we can split this as a over s plus b over s plus 1 over 17 plus c over s minus 3 over 16 plus, this is d over s minus 6 over 37. Please calculate. Please. 28.5. Yes. No problem. That's okay. Minus 204 over 455 over s plus 1 over 70. Yes. Yes, please. Yes. Hmm. Okay. Okay. This is 48.85 over s minus 3 by 16. Okay. Minus 28.77 over, this is s minus 6 over. So this means this is the C of s. Let's take the L inverse to get the C of t. So C of t is equal to 28.5 times u of t minus 204 over 455 e to the minus t by 17, correct? 1 by 17 t 48.55 e to the 3t by 16 minus this is 28.77 e to the 6t by c of t. Let's apply the condition, that is limit as the time goes to infinity c of t, right? First value is 28.5 into 1, okay, so that's I'll write here. So the next value should be minus 2 not minus 204 by 455. What happens to this term? E to the minus t by 17. To the next term, that is 48.55. Is it 0? Look at the, I think you need to consider the sign, right? So there is, it's a positive term. Okay, so what happens? Huh. So previously it was e to the minus infinity, right? This term was a 0, right? Now what happens to this term? E to the power positive infinity, right? What is that? That's equal to, I can replace it as e to the power large number is not 1. E to the 0 is 1, right? Correct? So e to the 0 is 1. E to the power 1 is e. E to the 2 is e squared. And like that. It's a big number, right? So when this becomes infinity, this will be infinity. It's infinity, right? Minus once again 2 point times infinity. So whenever you have an infinity getting added up to any term, the answer is infinity, right? So your result says that the system is unstable. So previously we got a finite answer, that's why we declared that system as stable. This is unstable. All right. Now, okay, let's look at the system. Why the system? Now here simply we write, if we write infinity, we might not understand what exactly is happening. Right. Let's compare what happens with this system and the previous system. Right. As the time progresses. Okay, that gives you a very clear idea about what exactly is happening. All right. Either we have to write a graph, otherwise we'll calculate first few values. All right. Okay. So maybe let's do this. Let's do a very small exercise to understand this. So this is our intention. I'll put a time here. So the previous answer I'm going to call it as a C1 of t. Okay, and the current C of t I'll go call it as a say C2 of t. Right? Equations anyway we already have. I want you to calculate when t equal to 0, what are their values. T equal to 1, say t equal to 2, t equal to 5, say t equal to 8, and say t equal to 10. Maybe this is sufficient to understand what exactly is going to happen. Fill this table. First equation, put t equal to 0, we get some answer, right? So the same thing, t equal to 0, put in the second equation, we get another answer. So both we will be calculating and we'll write over here. Okay. First one, final answer. Okay. This one. Yeah, uh, in the C of t, put t equal to 0 first, then put t equal to 1, t equal to this, like that. So this is for the C2 of t, and you have the equation for C1 of t. No, right? Okay, this is the C1 of t, the previous answer. Yes. Yeah, sure, sure, no problem. Please take down. Yes. Hmm. So first you calculate all values for C1, then we'll go to C2. Okay. First we'll fill the first column of the table. Okay. Okay. When you put T0, just check what happens to the second and the third term. I think you have not considered that. This is e to the 0, so this is 1. So you have a term 11 by 12 to be considered. So this is 1 by 4, right? You need to consider. Okay, okay, yeah. So first term is actually, this is not 0. This is 1 by 4, 1 by 4 plus something. Okay. First one, right? Point four this is 0. This one? C2. Okay, okay. This is 0.23. All right. It's same. It's same for every value. Correct, correct. If the coefficient is 1 by 4, it's 1 by 4 into 1. That remains same for every value of t. Yes. Huh. Okay. Okay. No problem. Tell me the value. Hmm. Sure. Sure. Oh, now let's go to the second column. Equal to 153, right? 0.65. Okay, let's calculate that is Yes. The tendency we can understand by just looking. Even if we plot, we see the graph, right? So this keeps on reducing as the time progresses. It keeps on reducing, whereas the second column we can see that this actually is increasing. So that's why this becomes a finite value of 1 by 4 at infinity, correct? At t equal to infinity, you can see that this is 1 by 4. That's what we calculated. And this goes to infinity. Huh. Because e to the power, right? Correct. Again, it's not a linear case. It's non-linear because the term which you are calculating over there is a e to the power number, exponential, right? So we have such graph coming up. Okay, so we understood that this is what exactly happens, right? When the system is at a given point, it might look stable because if you calculate only at t equal to say 10, we see that okay, both systems are stable. You get a finite value, finite input, I'm getting finite output. But as the time goes to infinity, one system tends to be unstable, other one is stable. Okay, now let's look at the stability criteria once again, right? Using the given transfer function. Okay, so now we see that in the transfer function. So okay, that's the term. Look, I'm looking. I'll define the terms once again. Okay, so this is called as the transient. This is a transient response, and this is called as a steady state. Correct. First half is a steady state. This is the first problem we solved as an example today. Okay, out of which let me look at the poles of the system because transients arise because of the system poles. Right. Look at the position of the system poles in this given equation. In the sense, the system pole corresponds to this. In the transfer function, whatever poles we have, right? If you try to plot these poles, let's try to do a quick right. Okay, one pole at minus 1.5 and another pole at minus 2.5. So this is the pole zero plot of the first system. All right, and this is a stable system, correct? Now let's go to the second case and let's try to plot the same thing over here. Right. So we will come to know about that because of this. Now, one pole at say this is minus 1 by 17. Another pole at 3 by 16 and maybe this is I think 6 by 37 is smaller maybe. Okay. I'll write here. Okay. Fine. So now you see that this system becomes unstable, right? So if you have even one pole, right, at the right half of the S plane, it generates one term, one infinite term over here, right? Every term which is on the yes, yes. Just because one of the term becoming infinite, right, results in the infinity for the whole answer sum. That's why the system becomes unstable. So the point that we understand from this discussion is that coming to the related to the stability of a given system, right? So the system's stability can be directly interpreted, right, is calculated by just looking at, if you see the position of the system poles on the S plane. So this is the point, right? Poles on LHS, left hand side of the S plane, the system is said to be stable. Okay, whereas if we find that the poles of the system on the right hand side of the S plane, the system becomes unstable. So we can draw one diagram for this whole concept. Okay, so this is the real and this is the imaginary part. Now if at all we find the poles, so it's in the color, okay, if we find that the poles are present on the left hand side, so that makes the system stable. Whereas if we find the poles to be present on the right hand side of the S plane, the system is unstable. This side is stable, this side is unstable. This is very rough definition, right? Again, we have a few more concepts to discuss. What happens if you have poles exactly on the y-axis? What happens if there are repeated poles? What happens if they are complex conjugates, and etc. Right? Those things will be the upcoming topics that will be discussed in the next class.